Hi guys, we meet virtually once more. This time around to pay attention to an interesting topic in physics, which is momentum. So today we'll be looking at momentum and energy. I hope you have been following up on the previous lessons, because as I say, you cannot learn these things by looking or by listening only. You have to sit down, as I am sitting down now trying to assist you. You must also sit down and assist yourself by doing the problems and just doing what is necessary. We all know what is necessary. So sit down, because I won't be able to cover all problems or most complex problems. I'm trying to cover introductory problems and intermediary problems that will be able to give you the feel and at least the idea of what is happening. So yeah, we start with momentum today. So the last time I dealt with equations of motion, and if you go to my wall, there is also, I think on the timeline of Wesley Guild SA, there is a lesson on Newton's laws. So this builds from that, from Newton's laws to equations of motion. Now we are dealing with momentum. So I assume that you are familiar with those concepts. So yeah, remember, from Newton's laws, we dealt with moving objects. We dealt with moving bodies. In particular, I remember in the first law of Newton, we deal with bodies which eventually, according to the first law, will come to a stop because they are disturbed by an external resultant force. And if you checked that lesson, you will remember that I said this was kind of revolutionary during the time. This was subversive, because the philosophy of the time was that bodies do not move forever. They will move and eventually come to a stop. But that stop was not explained. What causes that stop? With the dawn of the Italian Galileo and Newton, the Englishman, and I believe that you might find that some of these theories did exist in Africa. It's just that, of course, not everything is documented, but there is no reason to believe that Africa did not understand such things. But their contribution was that it's not that bodies eventually come to a stop, but the idea is that moving bodies continue moving up until there is an external force that disturbs that motion and brings that motion to a halt. So that's the law of inertia. So momentum is a closely related idea to this first law and probably second law, moving bodies, because every moving body or object has a property which we call momentum. So momentum is a property of moving bodies or moving objects or particles, if you like. So yeah, I mean, that is how I can try to give you an intuitive feeling, like to give you an understanding of what momentum is without resorting to equations. Momentum is a property of moving bodies. So each and every object or body which you see in motion, it has a property called momentum. And how is it defined now? I'm defining it to you. I'm giving it to you now mathematically. A momentum is defined as, so it's a vector. So I will put a head mv. Right? So that is how momentum is defined. So it's a property which is proportional to the velocity of the moving body. You see, that is why now momentum is a property of moving objects, and hence in its definition there is a velocity, because if the velocity here is 0, then this body is stationary, this body is not moving. But if the body is moving, then it needs to have some velocity v. All right, and momentum is defined as the product of the mass of the body and the velocity. So another way mathematically to write this is that momentum is proportional to velocity, and it's also proportional to the mass of the body, because the smaller the velocity, the smaller the momentum, and the smaller the mass, the smaller the momentum. So there is that proportionality. So this momentum, you can think about it, because mass can be thought of as a fundamental variable of objects. Like it's a fundamental variable. You can define mass fundamentally across all objects, but velocity are some form of derivative. So, as much as this is true, but this is the important one. So, because at some point you can assume a mass of 1. So, but the velocity, this is the one that is important. Momentum is proportional to velocity. As much as in the second law of Newton, F is ma, we don't usually pay much attention to the mass, because it's considered as a proportionality constant. But the reason I'm writing it out here is because if it is extremely small, then it will affect your momentum. But yeah, the variable that we pay much attention to is the acceleration. So here we say F is proportional to acceleration, and the proportionality constant is the mass. Even here you can think the mass as the proportionality constant. So P is equals to mv. So this is the definition of momentum. P, and momentum, as I say, you see I put a hat on top of it. It's a vector, and since it's a vector, it means it has direction. The direction of momentum is the direction of the velocity. So when you get questions on computing or calculating momentum, if you want to specify the direction is always the direction of the velocity. Okay, so yeah, I think as an introduction, that is what momentum is. So let's just put it into use. So let's see what we can do. Let's just start with a simple example. If you have a car traveling at 120 kilometers per hour, so this is a velocity. It's just not given in meters per second. It's given in kilometers per hour. You can convert kilometers per hour to meters per second, but that's not the exercise now. Now, what I just want you to notice is that if you have a car traveling at 120 kilometers per hour, and you have another car traveling at 60 kilometers per hour, if you assume the same mass, if you assume these two cars have the same mass, then the car traveling at a higher speed, at a higher velocity, which is 120 kilometers per hour, will have a larger momentum compared to a car traveling at 60 kilometers per hour. I think that is just clear. It's just still emphasizing the idea of proportionality, that momentum is proportional, directly proportional to the velocity. So the greater the velocity, the greater the momentum. And the opposite is true. The smaller the velocity, then the smaller the momentum. Okay, so now let's calculate the momentum just using that simple equation. And you can see this equation is simple. I don't expect that there's anything complicated here. The main point of everything that I was saying is just trying to explain that here is the equation of momentum. So maybe I might have said a lot of things, but this is the main point, right? And so now, let's take an example. A soccer ball of mass 420 grams is kicked at 20 meters per second towards Itumele Nkune's post. Calculate the momentum of the ball, right? Okay? And of course, it's Itumeleng Nkune because I'm a Buccaneer. So, I mean, those are the posts that all the balls should be going to. Okay, so what is the momentum? Simple. What is the equation that we use for momentum? P is equals to mv. Okay, so what do we have here? We have the mass of the ball, 420 grams. What is, but remember the SI unit of mass is not grams, it's kilograms. So we must convert from grams to kilograms. And of course, the word kilo means it's 1,000. So to go to kilo, you have to divide that by 1,000. So that should be 0.42. I mean, 0.42. And so that's the mass of the ball. So I'll just say mass of ball. And you have the velocity, which is 20 meters per second. And simple, calculate the momentum of the ball. You just, I mean, you don't even need to think here. You just plug in the values. And it's something like, so 8.40 or something. I mean, 0.4, so 0.5 is 1 over 2. So, yeah, this can be 1 over 3 of some sort, or 1 over 3.5. So, and what are the units of momentum? Since momentum is given as mv, mass multiplied by the velocity, the units of mass are kilograms and the units of velocity are meters per second. So it means the units of momentum, and usually it's kilogram meters per second. So our answer here should be in kilogram meters per second. Remember, this is what? A vector. So we've just, what did we do here? We just solved for the magnitude, but in which direction is the momentum? The direction of the momentum is the direction of the velocity. So that is important, right? And what is the direction of the velocity of this ball? Is kicked at 20 meters towards Kune's post. So this momentum is towards Kune's post. Towards, I'll write Itumeleng Kune's, IK's post. So, straightforward. If there is something that you've missed, pause it in your own time and just go back and see if you can make sense of that. But that should be straightforward. Okay. And let me take another example, just to cement this before I move on. Here's another example. The center of the moon is approximately 384,000 kilometers from Earth and orbits Earth in 27.3 days. If the mass of the moon is 7.35 times 10 to the 32 kg, what is the momentum of the moon? P moon. So you have this, so okay, what is good practice which we learn from equations of motion? Always write down the variables which you have. So what are the variables that we have here? We have the mass of the moon, 735 times 10 to the 32 kg. What else do we have? The center of the moon from Earth. Okay? And they say assume circular orbit. So we have to account for the fact that the moon is moving in a circular orbit. So this is not linear motion. The motion is circular. So we have to account for that. But we have the time it takes. So we have T for the moon to orbit the Earth. So it's 27.3 days. And what else do we have? We have the distance from the center of the moon to the Earth. So let me write, so I'll just write D, E, So ME from moon to earth, DME, it's 384,000 kilometers. And the SI, so this is D. So the SI units of this distance, it's meters. And here we've been given the distance from the center of the moon to the earth in kilometers. So what we have to do is to convert kilometers to meters. And of course, if we have kilometers, kilo means so if it's meters, meters will be even more. So it have to be 1,000 more. So even more zeros. I mean, so how can I find a way to? So I'll say just 3, 8, 4. How many zeros? So times 10 to the 8 meters, I think. But so this, you should not stumble over these. These are, so you can just use your calculator. I'm just converting 384,000 kilometers to meters because distance, it's SI units, it's in meters. So if you use this in kilometers, you will not get the full marks. You will get half or 20% of the marks because teachers and markers are very strict when it comes to units, right? And here time it's in days, so we still need to convert time to seconds because the SI unit of time is not days but seconds. Right? So how can we do that? 27.3 days. So what is 1 day? 1 day is 24 hours. So I think just and what is how many seconds in a day or minute? So I think I have to multiply by 60 there because you're moving from days to seconds. So you have to say from days you want to go to seconds. So what is a day? A day is 24 hours, but an hour is 60 minutes and a minute is 60 seconds. So I mean you have to do that conversion, and ultimately I think you should get to something like 2.36 times 10 to the 6 seconds. See? And you see these small conversions are very important. If you struggle with them, you will have a nightmare when you are writing exams or tests, because somehow examiners just like complicating stuff. Because I mean, I don't think what they are assessing here is conversion factors, whether you can convert, but still they give you the variables in awkward units. They give you in kilometers, you must convert them to meters. They give you in days, you must convert to seconds. So just to be sure about these, you must just make sure. So make sure you can handle these conversions. Just make sure you can handle these conversions because you need to work with SI units. Okay, so now clear, we have mass in kilograms, we have T in seconds, and we have the distance in meters. But this distance is from the moon to, like, if this is the Earth, to the center of the Earth, and you are told that this moon is making some circular orbit, like something of that nature. So if it's a circular orbit, it will have to complete a circumference C, and I think circumference given by 2 pi r, the circumference of a circle. Okay, so, and what is this r? This r will be this radius. So if this is the moon and that is the Earth, so this is a center line from the center of the circle to the circumference, to the circle itself, is the radius. And we are given that this is 384 times 10 to the 8 meters, that big number. So this will be 2 pi multiplied by that big number. And you should get something like, is it 242 times 10 to the 8. So these are things that you can also verify. But okay, why do you want to calculate this? Because this is the distance that will be covered by the moon. And now we can calculate what is the velocity, right? What is the velocity? And what do we need to calculate the velocity? You need the distance S over t. Remember at some point you had S is v over dx when we're dealing with equations of motion. So from this you can get v, the velocity, and what will be the distance covered is this circumference, this number, 242 times 10 to the 8 meters, all over the time, which is 2.36 times 10 to the 6 seconds. And now ultimately you can get your velocity to be around 1.02 times 10 to the 3 meters per second. Right? So this is a circular orbit. So this is the velocity now of the moon. Now you have the velocity of the moon. Since you have the velocity of the moon, you can just now put the final nail in the coffin. P is mv. You have the mass you've been given, 7.35 multiplied by 10 to the 32, multiplied by what? By the velocity of the moon, which is 1.02 times 10 to the 3, the number that you got there, and there you can get your momentum. I think it's around 7.5 exponent 35 kilogram meters per second. Okay. So someone might be asking, why did we calculate this c? We needed to calculate this c because we want to get the velocity of the moon. But this is a circular orbit. If it's a circular orbit, it means it completes one period in this fashion. So this is the distance that is a circumference, because I mean in circular orbit, for you to move from here all around to there, it's a circumference, which is 2 pi multiplied by r. And once we have that distance and the time it takes, and then we can calculate the velocity. So that is what made that necessary. So that is very important for you. If this is not straightforward, just pause and go back and check, why are we doing this? Remember, we were told this is assume a circular orbit. If this was, so this is what complicated this circular orbit. But these questions you would get, so better be able to deal with them, because it's not that tough. What is different is just that you must now calculate the distance, not linearly now, but using the circle, which is just the circumference. So such things you have to know, okay? And you might not really find in your introductory textbooks, because this is not a standard thing, but you should be able to deal with this. This is what is expected. Okay? Oh, yeah, okay. So that is the gist of it, of what momentum is. So now we can move now to the change in momentum. So momentum, as a property of bodies in motion, it can change, and you can think on top of your head about physical situations which can cause momentum to change. And I can just give you maybe a few. I mean, the first thing that I think about is that from the first law, but the thing is that with the first law, what might be changing the momentum is the external force. Newton's first law, which says a body will continue moving or being at rest up until there's an external force which acts upon it. So if you think about a body which is already moving and there's an external force which acts upon it, it might interfere with its velocity, either increase it or decrease it or set it to zero, just completely annihilate the motion such that the body becomes at rest and it becomes stationary. So it might be that, or you can think about maybe a ball rebounding against the wall. it can be struck as in this situation where a ball can be struck against the wall and it bounces back. I mean, of course, this instance of the wall, despite the fact that it will change the direction of the ball, it also interferes with the momentum. A car moving and the driver applying brakes, it comes to a stop, it changes velocity, it changes momentum. So any action on the body which can change its velocity, and it can change therefore its momentum, because the main important variable with momentum is velocity. So now we're going to deal with the change in momentum. And remember that momentum is given as mv. Right? So what will be the momentum, for example, in this scenario of this? Assume this is a ball of mass m, and also it's still the same ball, so still mass m here. Because if it rebounds against the wall, it doesn't change the mass. It changes the direction, might change the velocity, but doesn't change the mass. So what will be the momentum of the initial momentum of this ball as it travels towards the wall? So this would be given as, let me say, pi would be mvi. And for this scenario where the ball bounces off the wall with a final velocity vf, but remember, I mean, the mass is still the same ball, so the mass doesn't change. So here you have pf being mvf. So the change here, change in momentum p, would be given as m change in v. And this is m v final minus v initial. So you can think about the change in momentum as given. I mean, of course, the mass doesn't change, but the velocity changes. Right? And the changing velocity can be understood also in terms of forces. It can be understood in terms of Newton's forces, resultant forces. How so? If you observe here, you have change in P, which is M change in V. Okay? And this can be given as M, what is V? V can be given as A change in T. Why? This is because acceleration is given as the change in the average velocity over the change in time. So you can see, to make V the subject of the formula, you might have to say just cross multiply with change in T. You have change in V is A change in T. So you see that change in V can be substituted with A change in T. And look at what we have now. We have MA. And remember what MA is. MA is Newton's second law. F is equal to MA. The resultant force, or the net force on a body, produces an acceleration. So you see, this can be written as F net change in T. So this is change in momentum. I'm not sure whether that is clear. So I'm saying change in momentum can be given as the force, resultant force, multiplied by the change in time. So this is another definition of the change in momentum. And you can see from where does it come from? It comes from the fact that you define the change in variable normally, but then you observe that you have change in V here. It is this change in V that is able to transform this equation and give you it in terms of the resultant or the net force. Because this change in V can be written as the acceleration and the change in time. And mass multiplied by acceleration is force, second law. So just substitute there with F net, and that's the equation which you have there. Not sure whether that is making sense. But yeah, just maybe if this is not that clear, when the video is over, just go back to this section and just make sense of it. But I mean, we have that result. Okay. And so here we are considering a situation where a ball rebounces off the wall. There can also be a situation where a ball hits against a surface, whether a wall, say it's a rough surface or what, a rough wall, or an elastic wall, or you can think about those volleyball dividers which have nets, and such that you can be able to hit the ball against this surface and it doesn't rebound. It just falls to zero. It doesn't move. It doesn't rebound or continue moving. It just halted. It just comes to rest. This also is a form of change in momentum, because you're moving from a momentum pi, where you had a velocity vi, to a situation where the velocity, the final velocity is zero. And of course, if the final velocity is zero, it forces the momentum to be zero, because remember that momentum is a function of moving bodies. So now if the body is no longer moving, it collapses the momentum to zero. So I think that is just straightforward. But you can also think about a situation where there is a surface that your ball collides against, and then after it continues moving, whether at a decelerated or accelerated version or speed, but the main point is that the ball continues with some final velocity vf, not a final velocity of zero. So in this instance, of course, you will have change in p, which is the final momentum minus the initial momentum, and this can be written as the final momentum is change in momentum plus the initial momentum. I mean, there is nothing fancy there. I just transposed variables, just transposed it to the other side. And what is this saying? I mean, this is not complicated. It just says if a body continues, then there will be a particular change in momentum. But in this case, where the final momentum is zero, that will be zero. And you're not going to have this situation here. So in this case, where the body continues, you have some final velocity. And this is how you can determine that final momentum. If you have that change in momentum and the initial momentum, you can determine the final one. And that final momentum must be in the opposite direction of motion for the final momentum to be less than the initial momentum. So if the final momentum, meaning the final velocity, if the final velocity is less because now it has come across some obstacle, some surface, maybe it lowers its speed, then you will have that the final momentum will be less than the initial one. And in that case where the final momentum is less than the initial momentum, it means the direction of momentum is in the opposite Why? Because the initial momentum is bigger, meaning the direction must be the direction of that velocity. Okay, so just clean that up so that you are able to account for directions, not only magnitude, directions when you deal with these questions, because they will get you. Okay, so enough theory, let's do a problem. So a tennis ball of mass 58 grams strikes a wall perpendicularly with a velocity of 10 meters per second. It rebounds at a velocity of 80 meters per second. Calculate the change in momentum caused by the wall. Okay? So a tennis ball, have a tennis ball, we throw it, okay, we strike it against the wall, it hits it perpendicularly with a velocity. So we have an initial velocity there of 10 meters per second, with a velocity of 10. It rebounds at a velocity of 8 meters per second. So the final velocity is 8 meters per second. And we are given the mass. The mass is 58 grams. Again, we are given in grams, but the SI unit of mass is kilograms. So you must convert that to kilograms. So this should be 0.058 kilograms. It was just divided by 1,000. Okay. So, and the question says, calculate the change in momentum caused by the wall. What is the formula for calculating the change in momentum? M change in V. What do we have here? We have VF minus VI. Okay? So what's the mass? The mass is 0.058 multiplied by the final velocity is 8 minus 10. Okay, so this will be minus 2. So the answer you get here will be a minus number. I think this will be minus 1.04 kilogram meters per second. And remember, momentum is a vector. So this negative indicates direction, right? So 1.04 kilogram meters per second. If we take towards the wall as positive, negative will be away from the wall. So this will be away from wall. Okay. So what have I shown you now? I've introduced momentum to you, tried to explain how it works so that you understand it without equations, introduced equations, calculated momentum using an equation. Now we have moved and now we are able to calculate the change in momentum. So we have made a step. I hope that you are moving with me. Okay. So this is the change in momentum. So because moving bodies can change their velocity, and by virtue of changing their velocity, their momentum changes. Okay. And this question of showing that the change in momentum is given by the net force multiplied by the change in time, you might get it maybe to show it or to prove in a multiple choice maybe which expression is equivalent to change in momentum. Maybe is it 1, they give you maybe this one, and maybe 2, they give you maybe F net over M, and maybe 3, they give you F net over A or something, and they say choose. And of course, you can't choose if you can't show this. So I showed you this so that we close all the gaps and we're able to comfortably deal with momentum, because it's not really a complicated concept. Okay, so let's move on. So momentum can also change because of collisions. Because of collisions. So you can think about, a simple question one can ask: what happens to momentum when two objects or bodies interact or collide? Because in the previous sheet, we considered just one body bouncing off the wall or off a particular surface. So it was not a system of bodies. So now we are just turning the temperature just a little bit. We increased it just a little bit, and now we're asking what happens when we don't have one body, but we have more than one body interacting or colliding within the same system. And what do we mean by system? A system in physics, by a system we mean any physical configuration that we are examining. So any physical configuration that is under our study, what we are interested in, we consider that as a system, a physical configuration that we are studying. But more pointedly, we also have what we call isolated systems. And what are isolated systems? Isolated systems are those systems where there are no external factors. I mean, we ignore or we shut out all external factors or influences from the environment. There are no external forces or interaction with the surrounding. So that's an isolated system. Of course, an isolated system is not real. It's an ideal system. But that is what we do as physicists. We start by studying a simple system that we can be able to handle. And once we understand that simple system, even if it is ideal, and then we build from that, we start building complexities from that, which will explain or which will be closer to explaining the real world which we live in. So we will be dealing with an isolated system. So I want that to be clear and highlighted. An isolated system is where there are no external forces, or the system that you're dealing with does not interact with your environment. And what is the property of isolated systems? And of course, at the same time, I just said this system is ideal, not real. Why am I saying that? Think about the example we've just dealt with, where we throw the ball and it rebounds against the wall. We made calculations without accounting for gravity. We know gravity is always there. But we simplify our systems such that we approximate that gravity is very close to zero in such a case. But the reality is that it's never closer to the surface of the earth. But we assume those so that we can be able to explain, and we add back those complications later. So for isolated systems, the reason we insist on starting with isolated systems is because of their property. The property of isolated systems is that the total change in momentum in the isolated system is constant. It's always constant. So if you have an isolated system and you have changing momentum, the total change in the momentum of the isolated system is constant. Okay? So and how do we say that mathematically? In this fashion, right? So this is how we say that mathematically. But this assumes an isolated system. That's why I wanted to stress that you cannot have this in a system which is not isolated, where there are external forces. This will not happen. But where there are no external forces, the total change in the momentum is constant, because you only constrain yourself to what is within your system. And we can show that the total change in the momentum is constant. We can simply show that quickly. Consider these two soccer balls, S1 and S2. Assume these balls are moving in opposite directions. So VS1, you can see, is moving towards the right, and this one is moving towards the left. And what does Newton's second law tell us about this body, these two bodies, if they will interact somewhere there in the middle, ignoring all external forces? What we know is that there will be a net resultant force between these two bodies, right, which is given by M change in V over change in T. I mean, why am I writing that? Okay, maybe you can start by saying F is MA, and what is A? A is change in V over change in T. So this is the second law, right? Okay, but from here, what do we know? We have M change in V. What is that M change in V? We just dealt with the change, so this is the change in momentum over the change in time. So for these two bodies, we can write that expression because we know that where they interact, there will be a net resultant force which should be given by MA. And A is given by that. And A, from here, we can move to the momentum. Okay, because change in P is M change in V. That's why we have that substitution. And what do we know from the third law? Since we are only dealing with internal forces, there are no external forces. What do we know from the third law is that, so third law, so it's Newton. What do we know? What we know is that the force of due to the first ball will be equals to the force exerted by the other ball on the first one. Because remember, this is Newton's third law. If body A exerts a force on body B, then body B exerts a force of equal magnitude but opposite direction towards body A. So this is what's happening. That's why we have a negative. This is to denote the opposite direction. Okay. So, but what is F? F can be written as what? Newton's law, we wrote it up here. So here you can have M, velocity of the first body. I'm hesitant to say T1 or T2 because time is the same. So let's just keep time to be the same. So this is dV2 over T, assuming that they will, of course, they're governed by the same watch. So time is the same. So what do you have here? So here what do you have? So T will cancel dt, and ultimately you have M change in V1. If you transpose this to the other side, you have plus M change in V2 is equals to 0. But what's M change in V1? Look at that. M change in V. M change in V1. So this is just change in P1 plus change in P2 is equals to 0. And you can see 0 is a constant, right? C. So if you take these two, the sum of these two as the total change in this system, then we have shown that the total change is always a constant. In this case, the constant is 0. So where are we? So, what is this saying? It's saying if you add up all changes in momentum for an isolated system, the net resultant of those momentum will be 0, of those momenta. So plural of momentum is not momentums, it's momenta. So, the net result will be 0 of the momenta, change in momenta within an isolated system. Okay. So remember, here, isolated system is the absence of external forces. Okay? And I think while it's just at the same, while it's there, maybe I can, because now we have sufficient ground to define what we call the conservation of momentum. Conservation of momentum. Remember that we are still in an isolated system. So in the absence of external forces, for an isolated system, and this is important because if the system is not isolated, these results are not as we are. They won't look the way they look now. So we will not be telling the truth. So for an isolated system, we have shown that the total change in the momentum is a constant. And related to that, we can now define what we call the conservation of momentum, right? Which says for an isolated system, the total momentum of a system is conserved. Now we're no longer talking about the change. I mean, it can be, but we're talking about the total momentum. So for an isolated system, the total momentum PT is conserved. So what does it mean? It means you have PT being, let's say you have P1 plus P2. So this will be your total momentum. So this will always be constant. Another way of saying it is that this is conserved, right? So let's just take it, let's take it easy for now, because this also means that the momentum before the collision has to be equal to the momentum after the collision. Why? Because this is an isolated system. But if there is an external force, that might not be the case. Okay, so let's take an example. So with the constant change in momentum in an isolated system, we now also have the conservation of momentum, that the total momentum of an isolated system is conserved. And it can be calculated, of course, by the vector sum of the objects in the system. This is what is shown here. Okay, so let's take an example. Okay, so where am I? Okay, I'm just checking whether this is an example which, okay, fine. Okay, let's take this one. Okay. So a jet flies at a speed of 275 meters per second. The pilot fires a missile at a speed of 700 meters per second relative to the ground. The masses of the jet and the missile are 5,000 kg and 50 kg. Treat the system as isolated. Calculate the new speed of the jet immediately after the missile has been fired. So probably have something like this. From somewhere there, it launches a missile. Okay, so this is just a picture for myself. So it's flying 275 meters per second, and the missile is fired at 700 meters per second, and the mass of the jet is 5,000. The mass of the missile is 50. And now they say treat the system as isolated. What does isolated system mean? It means the total momentum is conserved. Right? It's conserved. Should be conserved. Change in the momentum of that system is constant, and the total momentum should, and when we say something is constant, we mean it is not changing. I mean, okay, I don't know where I showed this. Oh, it's here. Okay. We showed here that, I mean, the total change in momentum is zero, meaning it's not the momentum. If the change in momentum is zero, it means it's not changing, right? That's another way to think about it. Okay. So what have we been given here? We're also given the initial velocity of the jet, which is 275 meters per second. And we are given, I think we have the initial velocity also of, we have the velocity of the missile also. Okay. I think, so this would be the initial, and remember, initial velocity, since this jet is flying before it produces this missile, it means the initial velocity of the missile is also that. So this is initial velocity of missile, it is initial velocity of jet, because they are traveling in unison. The missile is in the jet up until the missile is fired, and then the V final of the missile will be 700 meters per second. And what does the conservation of momentum say? If momentum is conserved, it means the total momentum of the system, total initial momentum of the system, should be equals to the total final momentum. Because it's not changing. That is what it means. It means it's not changing. It means the momentum that you had started with, you also complete with. Okay. So what do we have here? Okay. So initial momentum before, so total P before is equals to total P after. In simple terms, this is what conservation of momentum means for an isolated system. The total momentum before is equal to the total momentum after. And this is the total momentum before, initial momentum, when the jet was still flying before releasing the missile. So what is that? So it will be the mass of the jet multiplied by the velocity of the jet plus the mass of the missile multiplied by the velocity of the missile is equals to the final velocity, right? Is equals to, the mass of the jet, which is not changing, multiplied by the final velocity of the jet. So I'll say VF. Plus the mass of the missile multiplied by the final velocity of the missile. And we have the final velocity of the missile. What we don't have is that. And this is what we need, the speed of the jet after the missile has been fired. So we have that. So when we have this equation like this, now it's simple. It's just a matter of substituting the variables which we have. And remember, I said here the velocity of the jet and the missile before the missile is fired is the same. So what you will have here, you will have to add the mass 5,000 of the jet and the mass of the missile, because we can take out the common factor of V, which is 275 meters per second, is equal to the mass of jet, which is 5,000, multiplied by VF, we don't have VF, plus the mass of missile, which is 50 multiplied by 700 meters per second, which is that final speed, or a speed which the missile launched at. So when you hear, it's a matter of just rearranging and getting your answer. Using a calculator, you only have numbers, you only have one variable here, which is VF. So when you hear, you can rearrange and make VF the subject of the formula, And you should get that VF is around 270, I think, 75 meters per second. Velocity is a vector. In which direction? Towards the direction where it was traveling. So you have to specify direction. Okay. So that's where we are. I hope that is clear. So just using the fact that this is an isolated system and evoking the conservation of momentum, you were able to determine the final speed of the jet. Okay. I hope we're good. Okay. Okay, now, so now let's just extend that a bit. We extend this a bit just before we move to impulse. In physics, we speak of primarily two kinds of collisions. We speak of an elastic collision. We speak of an elastic collision and an inelastic collision. So what happens in an elastic collision? In an elastic collision, what we have, you have the conservation of momentum, which is maybe, so I say total momentum before initial is equals to total momentum after, so I call that final. You have that, but not only that. So an elastic collision is a collision where if something happens, think about cars which collide, and then they don't only remain deformed, because when cars collide, energy is transferred, and the way energy is transferred might show in a deformation of a car. And you see that, this car has been in an accident because here it has a scar, or it is, it is messed up here, because that's the energy of the other car which was transferred to that car. But think about a situation where the car does not remain deformed, but it is able to remain back, actually to be restored to its original shape. So that is elastic. Like, think about an elastic band. You can pull it, but it can go back to its position. Or think about a ball, an elastic ball that you can press down and release and goes back to its position. So an elastic collision, we assume that it is such a thing where energy is not only transferred in terms of deformations, but those deformations can be restored back. So in the elastic collision, you have two things which happen there. You have momentum being conserved, and you also have kinetic energy being conserved. So momentum and kinetic energy are conserved here. And what is kinetic energy? Kinetic energy is the energy due to the excitement or of the particles, or how quick the body is moving. Because you can see it's K is given as half mv squared. So if you haven't seen this, I'm introducing you to this. This is called the kinetic energy. So the term is self-explanatory. Kinetic. So it's energy which is kinetic, energy in motion. You can see it as v squared. So it differs from the momentum by that factor of a half, and the fact that it has an extra v, which multiplies the v of momentum. Multiply this by v, to be v squared, which gives you the kinetic energy, right? Energy due to the movement of particles. And remember that momentum also is a property that is due to the motion of a body or particles. So in an elastic collision, we have these two, momentum and kinetic energy, being conserved. So this is what you need to know, that when you are told that the collision is elastic, you have been given another gift. And what is that gift? It is the conservation of the kinetic energy. Okay? And at the same breath, you can also think about an inelastic collision. An inelastic collision is where, of course, a car will remain deformed. You'd have to take it SMD, or have to go, it's beyond repair. I mean, there's nothing you can do about it. So that's an inelastic collision. So in an inelastic collision, you don't have the conservation of energy, of kinetic energy, but you still have the conservation of momentum. You still have that total momentum before is equal to total momentum after. And I call it initial for before and final for after. So what was I trying to stress here? I'm saying you have two different collisions. Be careful when you read your questions. You have two different collisions. You have an elastic collision. An elastic collision is where kinetic energy is conserved. And I mean, I assume you had two bodies, M1 and M2. How can we write that? Since kinetic energy is given by half mv squared, so this is half mv squared 1 plus half mv squared 2. So I'll say 1 initial, 2 initial is equals to half mv squared 1 final plus half mv squared 2 final. So that is what this equation means. Same way with the momentum 1, which is basically m1 v1i plus m2 v2i is equals to m1 v1f plus m2 v2f. Before, after the particular explosion or collision. So the point I'm making here is that when you have an elastic collision, you have both of those. So you have two equations that you can work with to get whatever you need from your system. And if you are told the collision is inelastic, forget about that. You don't have that. You don't have the energies being conserved, but you only have the momentum still, because this is a function of isolated systems. Okay. So let's take an example, and we are approaching the end of what we had to do today. So this is a bit of an involved problem, so just brace yourself. But it's straightforward, just that it needs some arithmetic, but it's straightforward. Consider two marbles. Marble 1 has mass 50 grams and marble 2 has mass 100 grams. Sipho rolls marble 2 along the ground towards marble 1 in the positive x direction. Marble 1 is initially at rest and marble 2 has velocity of 3 meters per second in the x direction. After they collide elastically, see, they are colliding. How are they colliding? It's an elastic collision. After they collide elastically, both marbles are moving. What is the final velocity of each marble? So let's start this again slowly. Consider two marbles. So you have two marbles, and the first marble M1 is 50 grams, and that is 0.05. I think it's supposed to be 0.5 kg. And you have the mass of marble 2. Marble 2 has mass 100 gram. 100 gram to kilogram is 0.1 kilogram. And so just divide that by 1,000. And you're told that, okay, they are moving in the x direction. Marble 1 is initially at rest. So the initial velocity of marble 1, so I'm saying v1i, is equals to 0 because it's at rest, not moving. And marble 2 has velocity of 3 meters per second. So marble 2 is 3 meters per second. And what else do we have? After they collide elastically, so this is an elastic collision. So elastic. So what does this mean? Elastic means that you have a conservation of momentum and conservation of energy. Okay. And okay. So these are our givens. We are given this. And what is the question? The question is, after these bodies collide elastically, these marbles, ama-ali. Not sure whether you guys know ama-ali. Mokhulele elokishini, you would know ama-ali. Besodlala nge-5 iron, 5 or 50 cent namajita. So, okay, anyway, so these are marbles. So both marbles are moving. What is the final velocity of each marble? So that's the question. What is the final velocity of each marble? And we've written down everything we have as we have learned from equations of motion, that write down your knowns. So how can we start here? Let's start with the converse. Okay. What's the question first? The question is the final velocity of each marble. Remember that. So we're looking for V. How am I writing this again? V1F, V2F. So these are our culprits. We are looking for these guys. We must look for them and find them, of course. Okay. So let's start with the conservation of momentum. Let's see what we can get from the conservation of momentum. Okay. So what can we get from there? Okay. So we are writing an expression for the conservation of momentum. We have two marbles. So what does this mean? M1 V1 initial plus M2 V2 initial should be equals to M1 V1 final plus M2 V2 final. That's what we have from the conservation of momentum. And what are we looking for? We should always keep that in mind. We are looking for the final velocity of both marbles. So we are looking for V1F and also for V2F. Okay. So from this expression, what can we do? We know V1I is 0. The initial velocity of the first marble is 0. So this part will collapse. So 0 will collapse this part. So you'll have M2 V2I is equals to M1 V1 F plus M2 V2 F. Okay. And from here, and from this expression, you can see that you can be able to write V1 final or V2 final as the subject of the formula, because these are the culprits that we are looking for. So let's write it for V1F. So V for V1F, so simply transpose that to the other side and divide by M1. So what we'll have is M2 all over M1 multiplied by V2I minus V2F. Okay, so I'll call that equation 1. So this is my equation 1 from momentum. So this is the expression I have from the conservation of momentum, right? Okay, and now from the energy, what can I have from the energy? Okay, from energy, I did show you the expression for the kinetic energy. So total kinetic energy before will be half M1 V1 initial squared, remember it's squares, plus half M2 V2 initial squared is equals to half M1 V1 final squared plus half M2 V2 final squared. Again, we have V1I is 0. So that term is destroyed again, and we can multiply by 2 across and get rid of the half. Then you'll have M2 V squared 2I is equals to M1 V1F squared plus M2 V2. Okay? And when we here, you can write this as equation 2. And you can see you can substitute V1F in this equation and get the expression for V2. Think about that. You're looking for V1F and V2F. You have two equations and two unknowns, simultaneous equations. You can substitute that V1F in this equation and get V2F. And when you got V2F, you can substitute it back to this equation and get V1F. Simultaneous equations. Okay. If you are not sure about functions, check out my wall in the coming weeks. I'll be dealing with functions. From the foundations and to the functions needed in grade 12. So when we hear, what can we do? Do as I say, substitute V1F here. And ultimately what you will have, V squared 2i will be M2 over M1, V2i minus V2f all squared plus V2f squared. Okay, so when we hear, what can we do? We can transpose that V2i, right? Transpose and substitute M2 and M1, because we have these numbers. We have M2 is 0.1, M1 is 0.05. So you can make those substitution and then ultimately what you'll have is a quadratic equation here. And you'll have an equation that looks like 3v squared 2f minus 12 v2f plus 9 equals to 0. So you have a quadratic equation. Quadratic equation, how do we solve a quadratic equation? X minus b plus minus the root b squared minus 4ac all over 2a. You have a quadratic equation there. Or you just simply factorize. And with this one, you can easily factorize and you'll get v2f minus 3 multiplied by v2f minus 1 is 0, meaning v2f is either 3 meters per second or v2f is 1 meters per second. Right? You have two values. Right? Substitute back, take these values, substitute them back here, each of them, you will get that V1F is 0 or 4 meters per second, and we know it has to be 4 meters per second because we are told it's moving, and you can determine the direction. I think it's towards the right. So it's moving. So it's not 0. You get two values when you substitute back there. You get two values of the velocity, but because we are told the marbles are moving, it cannot be 0. It has to be 4 meters per second. Okay. So that is quite an involved problem, but as I say, it's an easy problem. You just have to be able, like, yabona xa udila ne-maths ungoyiki le notation le. Indlela ebhalwe ngayo lento, these variables zizo ezoyikisa abantu. So abantu abaninzi, the main problem abanayo nge-maths, it's the notation, not the actual concept. So I'm saying the concept is straightforward. Just work through these things comfortably and get the answer. And if you do struggle, just make sure you drop Wesley Guild essay in inbox and we'll look at it. Right? But do your problems. So I've done half of the work here. Okay. Okay. So now let's look at the last concept of impulse. So we'll take the last 5 minutes. My camera lady here, Bubla, my wife, is tired now, and she's the one that always assists me with these videos. So we owe her some chocolates. Okay. But let's just close this so that we know that at least we've closed this part, right? With momentum, there's a closely related concept of momentum which is called impulse. And what is the impulse? The impulse simply is the amount of time it takes when the force is acting in a particular body. So the time it takes for a force to act on a particular body. What is it called? An impulse. So, yabona, if you hit someone with your fist, depending on how long your fist stays on their face, you can calculate that the force which you used with your fist, the newtons in your fist, and the amount of time your fist spends in the face of your enemy or your adversary. You can calculate the impulse using that time in the force, right? So, as I say, it's basically the amount of time for a force to act in a particular body. So I can define it as IM is just the resultant force multiplied by the time. So this is the impulse, right? But remember earlier, I showed you in the other sheet, that actually the change in momentum can be given as the multiplication of the resultant force and the time it takes for this force to act. Remember that equation? It will come in handy now. What do we know about F net? So F net is change in momentum over change in time. So multiply by, and where does this come from? This comes from the fact that change in momentum can be given as F multiplied by change in T. F net multiplied by change in T. So we simply use this in here. And what does this mean? Change in T cancels change in T. And ultimately, we have that impulse actually is the change in momentum. It's nice doing these physics equations, how they alternate, how they speak into each other. Now we have another concept called impulse, which we are told that actually this concept is the same as just the change in momentum. You understand? So we have this, and let me just demonstrate how it works. Take an example where you have 150 Newton resultant force acting on a 300 kg trailer, right? And now the question says, so what do you have? You have a net force, F net, 150 Newtons, and you have a mass of a trailer, MT, 300 kg, so we don't need any conversions here. Anyway, the units of force are newtons and the SI unit of mass are kg, so we're good. Okay, so, and the question is, how long does it take this 150 Newton force to change the trailer's velocity from an initial velocity of 2 meters per second to a final velocity of 6 meters per second in the same direction? 150 Newton resultant force acts on a 300 kg trailer. Calculate how long it takes this force to change the trailer's velocity from 2 meters per second to 6 meters per second in the same direction. So you have those. So what do we know? We know that F net change in T is equal to the change in momentum. Right? And change in momentum in this case is M. Okay. Vf minus Vi, because what is changing is the velocity. Right? So this means that, remember, you are looking for how long, so you're looking for the time, how long. So we want change in T as the subject of the formula. So we have change in T is equals to M Vf minus Vi all over F net. And what is F net? F net is 150 Newtons. So, and what is M? So we have 300 kg, 6 minus 2 multiplied by 4. So this is 200 all over 150. 1 over 150. So this is 8 seconds. So how long does it take? It takes 8 seconds. Okay? And simple, this is just applying the concept of impulse. I don't think it can get worse than this. Here's the last one just to take it home, which is a typical test or exam problem. A cricket ball weighing 156 grams is moving at 54 kilometers per hour towards a batsman. it is hit by the batsman back towards the bowler at 36 kilometers per hour. Calculate what? The ball's impulse, and calculate the average force exerted by the bat if the ball is in contact with the bat for 0.13 seconds. So we start with 1. What is the ball's impulse? We know impulse is given as change in P, right? We showed it, right? This change in P is from this expression, right? Okay. And we know change in P means this, final momentum minus initial momentum, which is that, right? And we have the mass, cricket ball, so I'll say mass of ball 156 grams, so it's 0.156 kilograms. And what else do we know? We know that it is moving at 54 kilometers per hour. So VI, VI 54, so 54, we need to convert kilometers per hour to meters per second, right? So this will be supposed to be 54. 1 kilometer is how many meters? 1,000 meters per 1 hour. So per means divide by hour. What is 1 hour? How many seconds is 1 hour? 3,600 seconds. And this is 15 meters per second. So we have the initial 15 meters per second of this cricket ball. And we know the final velocity because it is hit by the batsman back towards the bowler at 36 kilometers per hour. So we have VF 36 kilometers. So here I'm doing the conversion. So 36, 1 kilometer is how many meters? 1,000 meters over an hour, 3,600 seconds in 1 hour. And this will be 10 meters per second. So we have VI 15 meters per second, V final 10 meters per second. Now you can calculate the change in momentum, which is mVF minus VI. 0.156 is the mass. Final velocity is 10 minus 15. So you'll get a minus. Okay, so this initial velocity, one of these two velocity must be in an opposite direction, right? Because it is bowled towards a batsman. If you take that as positive, when it is hit by a batsman backward, that will be negative, or vice versa. So this can be negative 15, and ultimately you have this as maybe 3.9 kilogram meters per second. So that's your change in momentum. It's given by 3.9 kilogram meters per second. And what's the direction? The direction is that of the velocity. So this is what? Towards the bowler, because we took the other one to be negative. So just make sure of your directions. And the last question is calculate the average force exerted by the bat if the ball is in contact with the bat for 0.13 seconds. So I'm not going to do this one for you, but it's easy because, I mean, you have impulse, it's F net multiplied by change in time, which is the change in momentum, and you have seconds, which is the time. You need the force, you have the change in momentum, we just calculated it, and then you can calculate the average force which is needed there, and it should come to around 30 newtons. So yes, please do more problems. That is it though for today. It's been quite a long lecture, but it's very important. The concepts are not that difficult. Give yourself time because we are still in lockdown. Go through it again. It's always good to do some physics with you. So stay safe, free from COVID-19. Obey the rules. Pray. This is from your personal tutor, Cozy Mental, and I wish you all the best in your studies. Thanks for today. Bye.